directional derivatives and gradients. Those are the last sections that we went over. And try to remember the two really important properties of the gradient. As one is that they're the direction of the fastest increase, and then the second one is that they're perpendicular to a level curve. And then you'll see when you start doing some homework assignments, you'll hopefully be able to compute them, but also be able to interpret the pictures. There's one picture that I wanted to talk about. Maybe I'll talk about it without showing it to you. But it's like, you know how we think of level curves as the, what do you call it? Contour maps of a terrain. And then the path of a river, if you look at a river on a mountain, the path of the river, as water going down the side of a mountain, it's going to look for the fastest way to get down the mountain. So if you imagine the path of the river and draw the contour curves on the map, you'll see that the river would be flowing from each of the contours. Your river will be flowing in the opposite direction of the gradient, and it'll be perpendicular to the level curves. So there's pictures like that in the book and the homework assignments, and I think in the exercises you'll see pictures like that. So if you look at the flow of the river with the contours, you should see that there's some gradients involved there. All right, today we're going to talk about max and mins. And we're going to define it. Now, the definition is one of those definitions where it'd be nice if you're a math major, you really need to dig in and try to understand this. But if not, it's not that big of a deal. It is kind of intuitive, but the symbols in this definition make it look kind of weird. But if we break it down and really talk about it, it should make a lot of sense. So let's start with a local maximum. A function is a local maximum if all the points around it will give you other points less than the actual maximum value. So just a simple graphic of this that you can think of would be if you have and we don't need the whole surface. If you just take a look at a piece of a surface, and then this is your maximum value up here. What they do is they relate this to what's happening in the domain. So if you look in the domain, this would be your point AB. And then f of AB, you see f of AB all over this definition. F of AB is a z-value. It's a scalar. It's a number. It's a z-value that tells you the height. And what we're saying is that this is the actual height of the maximum. And they say that if you pick any other point near AB, if you pick any other point xy within this domain, or if you pick any other point xy near AB, then when you put that into the function, you're always going to be less so regardless of what value you put in, these are all samplings of some random xy points that we're selecting near AB. If we put that into the function, then your output value, your z-value, will always be less than f of AB, because that's the maximum. So that's what this is saying. So a function of two variables has a local maximum at a, b, so this is the maximum. Maximum at a, b. If f of xy, that's any xy you put in from the domain, as long as you're near a, b, when you put that into the function, f of xy is going to be less than f of a, b. And you'll see that on the z-axis. This means that f of xy is less than f of a, b for all points in some disk. And so here in math, they always define the domain as some sort of disk. Now, I know back in calculus, our life was a lot simpler because we just had one input and one output. And so if you had some a value over here, and then you found the maximum at a, and then you choose other points near a, put it into the function, you're going to get f of x is going to be less than f of a. So that's the same scenario over here. And then what they talk about here is a small little interval near a. So this little interval that they talk about, well, we call it an interval, but you can also think about that as a disk. This is a small disk. Of course, it's a straight line, so you can't really think about it as a disk, but so people say interval. But in 2 dimensions, when your domain is 2-dimensional, then you're talking about a circular disk to describe all those numbers within there. And this idea of the radius of convergence, have you heard that before? The radius of convergence comes from this idea of a disk. Now, back in Calc 2, we just usually look at it as an interval of convergence, right? But it has something to do with the radius because we're always looking at values that are equidistant from the center. And in one dimension, in this one-dimensional domain, it's just going 2 different ways, so it looks like an interval. But in 2 dimensions, then you have something like this, where it's a disk. And in 3 dimensions, now you're at a ball, a sphere. 4 dimensions, you're in a hypersphere. Whoa. So this is what they mean by disk. The number f of a, b is called the maximum value. So the maximum occurs at a particular point, but the actual value is the scalar value that gives the maximum value. So max value is that number. So depending on how they're asking the question or what they're asking, they might ask you where is the maximum occurring, or where's the maximum, and then they might ask you what is the maximum value, in which case you would give the maximum value. Okay? So we turn one inequality around, and then you get the same story for the minimum, and the same picture, except it's turned upside down. Notice they want to talk about values that are near that point, and when they say near, they're still a little bit vague about that. That's because if you go far enough away, there are some functions where maybe this function goes up and eventually gets higher. So if you go far enough away, there might be something that's bigger than that. And so the same thing happens here. If your function happens to go up, and then if you go far enough away, then it could give you a value that's bigger than what you had as a maximum. But that's why this is called a local maximum, because within a small domain of it, that's the largest value. But outside of the small domain, you might get other maximums that are happening. So this is a definition for a local. Okay? So what's interesting about this? Well, in terms of calculus and derivatives, what can you say about the derivative? Well, what can you say about the derivative up here for back in Calc 1? What's the derivative at this point? As derivatives equal to 0, right? So df dx, or I should have just said f prime, evaluated at a is equal to 0. So your derivative is equal to 0 at that point. Well, it's going to be the same idea over here, except we don't have just a regular derivative anymore, right? We have partial derivatives. And so all we really have is a derivative like with respect to x and with respect to y. But if we take a look at the derivative with respect to x or with respect to y, what can you say about those? To each other, which is equal to 0. Should be equal to 0, right? If you're right on top of the mountain, you know, if you're right on sitting on top of the mountain, and then you put an arrow that's perpendicular, not perpendicular, but if you put an arrow that's tangent to the mountain going in one direction and going in another direction, they should all have 0 derivatives. So that's our little theorem that's coming up next that says if it has a local max and min, then the partial derivatives must equal to 0. We're going to stay away from weird functions where the derivative might not exist, or where the derivative, some weird thing happens with the derivative. Remember the definition of a critical point back in Calc 1 was like the derivative is equal to 0 or the derivative does not exist. We can talk about where the derivative doesn't exist here, but we're not actually going to dive deep into that. We're just going to take a look at where derivatives are defined. So we're going to want our derivative to be defined, and we're going to say that both of the partials will equal to each other and will equal to 0. So if you go backwards, remember that the weird things happen where if you say that if the derivative does not equal to 0, does that mean that you don't have a local max there or a local min? And that's a false statement, because if your derivative doesn't exist, then you might have a sharp corner or a point or something like that. And so we'll not worry about those cases for this class. Now, do you remember how we used to check for max and mins? There's 2, right? Yeah. There's a first derivative test. And then there's a second derivative test. Let's talk about both of these from calculus. What was the first derivative test? You guys remember? Really? Come on. Okay, Matt.
If I remember correctly, first derivative test involves us setting each of the derivatives equal to each of the first derivatives equal to 0.
Well, let's just say
back into the original
this let's not worry about the partials. Let's do this in Calc 1. So f r to r, and then so what do you do? F prime equals 0, and then what?
And those would be like the candidate points. And then plug it back into the original function.
You lost me there. So we set x equal to 0 and we solve for x, and we find these candidates. I think we used to call them critical points. Test points around them. Oh boy, that's really crappy. You guys can read that, right? So we find critical points. Test points around the critical points. And then you can see if it goes up and down, then you have a maximum, or if it goes down and up, you have a minimum. Or it could possibly go up and up, or down and down. I think those are all our options. And that's how you would identify the max local min. And this is neither. And most of the time it ends up being what? What are those things called? No. What? No. No, we're not talking. Let's not talk about piecewise functions. Let's make this. These are nice functions. No. Yeah. What's that called? That point where concavity changes. No. Inflection. So sometimes, or most of the time, we see these things, and then they end up being inflection points. Saddle will be coming up soon. All right. So this is a nice idea. The whole first derivative test idea. But we can't do this. For this type of function. Great idea, but cannot be applied to a function that takes two variables and gives out one value. Why not? Any ideas why not? Not necessarily. So if you try this in a three-dimensional surface, what's happening? Like this is a local maximum right here. This picture that I drew is a local maximum. So why can't we use a first derivative test where we have a point and then we have this candidate. Let's say we took the derivative, the partial derivative, set them equal to 0. So we have this as a candidate for possibly being a local maximum. Now why can't we just plug in some points like the definition says, right? Plug in some points from here and then see what happens. Why can't we do that? Yeah? Because multiple planes intersect that point. Yeah, so if we cut it with one plane, you might get a maximum. If we cut it from another plane, you might get a maximum. But if you cut it with some other random plane, then you might get a minimum, or you might get nothing. Right? Yeah?
Couldn't you also think of that in a way, if you intersect that with an infinite number of planes in that, that small space, then this calculus doesn't work.
Because if you intersect it with like an infinite number of planes, it would make this possible or impossible?
I was asking if it would be impossible.
Not that it would be impossible. The impossible part is how many planes do we need to cut it with? An infinite number of planes. That's what makes it impossible. Fifi, what were you going to say? What? Say it again? What curve? Oh, level? I suppose we could try to see it using a level curve. That can help us, but there's still might not be a guarantee. Wait a minute. I never thought about that. You could see maximums and minimums using level curves. That's true. Good suggestion. Yeah. Yeah, I think that might work for something like this. I'll have to think about that and see how it would work. I've never seen it presented like that in the calculus textbook before, but let's see. Anyways, I was hoping that I would remind somebody of limits. How to prove that the limit doesn't exist, you have to find two paths and then be able to conclude that the limit doesn't exist because you get two different answers. But if the limit does exist, that's impossible to check. You know, in Calc 1, you will get the limits to exist by just going from one direction and going from the other direction. So there's only two directions to get to. But in Calc 3, or when we're talking about this in 3 dimensions, there's more than one way. There's more than two ways to get there. There's an infinite number of ways to get there. So the bottom line is we can't use the first derivative test to find maximums or minimums, to find local maximums or minimums. Okay. But the second derivative test can be extended to higher dimensions, it turns out. Now we just have to remember what that says. What do you guys remember from the second derivative test? So it starts off the same way. You're going to find critical points. No, you don't care. I mean, it'll help to check what's around it, but you're actually checking the exact point. So you're actually putting your critical point, P, whatever your critical point is, directly into the second derivative. And what? Yeah?
So if that equals 0, isn't it just a measure of flat?
Yeah, yeah, but no. So imagine this thing is being a critical point, which means it has a slope is equal to 0, right? If it's what?
If the second derivative is positive, then it's a min because that means it's curving up.
So if the derivative is positive, then that means second derivative. The second derivative is positive. That means it's concave up, and this is a critical point. The derivative is equal to 0, so it has to be a minimum. Then x equals p is a local minimum. And then, likewise, if it's less than 0, then x equals p is a local maximum. Now, a lot of you guys were talking about what happens when it's equal to 0. What happens when the second derivative is equal to 0? It could be an inflection point, but not necessarily. So that's the weird thing about this stuff is that if you look, I like to use x to the third and x to the fourth as examples, and find the derivative and find that it's equal to 0 at 0, and the second derivative is equal to 0 at 0, and then we have an inflection point for x to the third, but x to the fourth is actually a local minimum. And so, well, we don't have saddle points in here, but we do have saddle points when we go into our next topic. Yeah. No, that it gets a little bit more complicated. There's going to be some saddle point issue. The rate of change. Yeah, you can't say anything. So the unfortunate thing about the second derivative test, and probably why we don't use it as much as the first derivative test, is because there's a possibility that we get no conclusion. For the first derivative test back in Calc 1, we can always tell whether something's a local max or local min because we can see how the graph will look like as we move along the x value passing through that special critical point. But for the second derivative test, you can't tell. So an example for this is that if your function is x cubed, you have neither max min but if you have f of x is equal to x to the fourth, you have x equals 0 is a local min. And then if you want, you can do a third example where it's negative x to the fourth, x equals 0 is a local max. So these are all examples from Calc 1. And like I said, we probably don't use a second derivative test very often because of the fact that we might get no conclusion for our results. But in terms of an extension to higher dimensions, this second derivative test will extend things for us. And so we can actually get a, well, we can get stuff, find some conclusions. All right. So these are all flashbacks. This is all from Calc 1. Right? So now let's come back to Calculus 3 and talk about our second derivative test for Calculus 3. So just like in Calc 1, the second derivatives test starts off by finding critical points, which we probably need to practice finding critical points for functions of more than one variable, because it's a little trickier than finding a critical point when you just have an f of x is equal to something, one variable. So when you have two variables, you actually have to set two things equal to 0. That's your fx and your fy, your partial derivatives. And then solving for that's a little tricky because you have two equations and two unknowns to solve for. But once you get past that, you have your critical points, point or points, depending on the type of function you have. And so the second derivative, well, there's 4 second derivatives, it turned out, right? fxx, fxy, fyx, and fyy. So there's 4 second derivatives that are involved here. And what we want to do is we want to use the signs for all 4 derivatives, second order partial derivatives, and try to include that into a nice compact formula. So the compact formula happens to be this. This is sometimes called a discriminant. Does it say there? No. Sometimes called a discriminant. That's why they call it D. And then it involves fxx, fyy, and then fxy. Where's fyx? In the FOIL? Kind of. If this is a nice function like we're claiming it is, fyx is equal to fxy. For nice functions. And so it turns out that this has all 4 second order partial derivatives. In fact, we can actually write this compactly into a matrix of second order partials. fxx, fxy, fyx, and fyy. And then think about the determinant. Remember how to find the determinant? You multiply through the diagonals, fxx times fyy minus fxy and fyx. And if fxy and fyx are equal, then that just turns out to be fyx squared. So finding the determinant of this would give you our discriminant. Or you can call it determinant. Or some other math term that begins with a D. Denominator? Well, probably wouldn't call it a denominator. A divisor or dividend. What else starts with a D? Disk. Directrix.
Oh, obviously it's just a derivative.
This is the derivative. I'd stick with these two. Yeah.
I'm a little confused about what's taken in that those conditions right there.
Oh, one of them should be different. All right, which one is different? Damn it. Well, that's what happens when you copy and paste stuff. Let's go with this one. Let me change it in my notes. Okay, so here's the deal. If your discriminant is bigger than 0, and at the same time, if your f(x(x) is bigger than 0, then we can think about that as a positive contribution to the second derivative. And with a positive second derivative, we see this as being concave up, which means we have a local minimum. If the discriminant is bigger than 0 and the f(x(x) is less than 0, then in effect you have a negative discriminant or negative second derivative contribution, and we can think about this as being concave down. And concave down, if you look at concave down, the critical point must be at a maximum. So I forgot the term, positive something. There's a word that comes after positive or negative something with matrices that I can't remember off the top of my head right now, but that's what makes it positive and negative. If your determinant itself is negative, then there's something stranger happening. That's when you get a saddle point. In the book, they say it's neither a local max nor a min. It actually turns out to be a saddle point. And the book doesn't include D either, but I'd like to put that there to stress the fact that if your discriminant is actually equal to 0, then there is no conclusion you can make about this point being a local max, a local min, or a saddle. It could be a max, it could be a min, it could be a saddle, and we don't know because this particular second derivative test does not tell us that information. Okay? All right. So we've talked a lot of theory about this already. Let's actually try to do an example problem. So the example problem will ask us to come up with several steps, and the first step is to find the critical points, which again, it's not necessarily an easy thing to do. Let's do this first one. Wait, maybe that's a homework problem. Ah, that's a good one. Let's do it. Well, this problem is asking us to use a level curve, but They gave us the function, so I think I want to just use the function for now, and then we'll inspect the level curves after we do this problem. So we'll do the second derivative test, and then we'll do this. We'll take a look at this using the level curves, and then we get the comparison. All right, so our first step is to find critical points. So CRIT is short for critical points. We can just use CP, I suppose, but I use critical points. And we need to find a derivative with respect to x. This is going to be 3x squared minus 3y. And the derivative with respect to y, which is going to be 3y squared minus 3x. Now, this is where it gets a little tricky. We want to solve for this two equations and two unknowns, and so whatever x, y pair that we get, it has to satisfy that these both are equal to 0. So they're not, oops, there's a square, extra square here. They're not linear, so we can't do anything like with, you know, those addition rule or substitution. Oh, we can do substitution. So let's do some sort of substitution thing here to try to solve for this. So I can cancel the 3's out and then say y is equal to x squared. And then I'll put that into this. I can also cancel the 3 out and say y is equal to x squared. So this is going to be x squared squared. I'm going to put the y in there. Minus x is equal to 0. Maybe if I change the color in the inside, it looks like I'm making that substitution. And then I continue to solve for this. I got x to the 4th minus x is equal to 0. And you've got to be careful when you solve for these things that you don't lose any values. Like if I divide by x, I'm automatically eliminating, in looking for something, I'm automatically eliminating the idea that x might equal to 0. So the best way to do these things, especially for nice polynomials like this, is just a factor, and then you can get the whole complete list of things that you might need. So I got x is equal to 0, and x is equal to positive 1, I think. And you can't be negative because it wouldn't work. And you know there's two more solutions that are complex, right? Makes me want to talk about some other stuff. Maybe I should go in a math club and talk about complex numbers there. They're called roots of unity. It's kind of cool. Anyways, these are the only two real solutions we got. And we can put it back, and it has to satisfy both equations, so I can put this back into here to get my y values. So when x is equal to 0, I got y is equal to 0. When x is equal to 1, I got my y is equal to 1. So these are my pairs that'll make up my critical points. So that's the first step. Okay. The next step in the second derivative test is to find the discriminant, the determinant, whatever you want to call it. And so we need to find 3 things, actually 4, but remember 2 of them are equal, so we can check that they're actually equal to each other if we want. But we need to find fxx, so you go to fx and take the derivative of this with respect to x. So 3y is constant, and this will just become 6x. fyy, maybe I should write it like this. So fxy, I want to take the derivative of fx with respect to y. This is 3x squared is constant. I have a negative 3 times y. So that's just a negative 3 after you take the derivative with respect to y. And just to show you that fxy and fyx are actually equal, I can go to fy and then take the derivative of this with respect to x. And 3y squared is constant, so that's gone. So this is again negative 3, which we knew. And fyy is going to be 6y. Okay? So our discriminant would equal to 6x times 6y, let's just call that 36xy, minus negative 3 times negative 3, or negative 3 quantity squared, positive 3, or positive 9. But there's a negative in front built in, so this will end up being 36xy minus 9. All right, we found the discriminant. Now we take each of our points, and you have to run each of your critical points through this discriminant one by one. So we're going to check the point 0, 0 into the discriminant. D evaluated when x is 0 and y is equal to 0 is equal to 0 minus 9, which is less than 0. Now this is option C in the list that I gave you. So must be a saddle point. 0, 0 is a saddle point. Okay? So that's one of them. The other point that we need to check is the point 1, 1. And D of 1, 1 is equal to 36 times 1 times 1 minus 9. Okay, so now that this is positive, we want to check what happens with fxx. And we want to put 1, 1, 1 in for x and 1 in for y. And if we do that, we're going to get 6, which is bigger than 0. So we have essentially a positive concave up graph at 1, 1. So what does that say? Say what? Local min. Okay? So those are our conclusions. For this problem. Now, if we actually want to find a value, what do we do? Plug it back into the function. Plug 0, 0 into the function, plug 1, 1 into the function. And then we get, well, actually, plugging a saddle point to the function is not too interesting, but to get the height, or in this case, the lowest point, you can plug 1, 1 into the original function, and then that'll tell you how low your maximum is, or your minimum is. All right? So let's actually take a look at the level curve and see how our results worked out. Here in these level curves, they're actually nice to give us the information. By that I mean the levels, the heights. So here's good ways to try to look for, by looking at level curves, look for max and mins and saddles. Usually when you have something enclosed in a circle, this is a feces comment about using level curves. Somewhere in here, in the middle of this thing, will end up being our local maximum or minimum. And then you can tell this is 3.7, this is 3.2. So as you go further and further in here, you're going to go 3.7, 3.2. So it's getting less and less, right? So this would be some y or some z value less than 3.2. So this is going to be a local minimum. At 1, 1. And by looking at the graph, this is more or less a guess. We don't know if it'll actually land right here exactly, but we did our analysis using the actual function, so we know that it's 1, 1. And now to check for saddles, if we see like hyperbolic behavior around a particular point, and usually you get values from one piece of the hyperbola compared to the other piece of the hyperbola, you have values that are differing. So this is 3.7 over here, and these level curves over here, if you follow this, this is 4.2 also. So these values look like they're a little bit less and a little bit greater than this actual point. Then you have a saddle. So our classic saddle is that hyperbolic paraboloid. And if you remember, the cross-sectional cuts for the hyperbolic paraboloids are hyperbolas. That's why it's called hyperbolic. And so with those hyperbolas around it, that actually makes it into a saddle point. At 0, 0, with a z value between, in this case, 3.7 and 4.2. So we never really checked our original function, but if you put 0, 0 into the original function, you know, that's simple enough to do. Our original function is 4 plus a bunch of zeros if you put 0, 0 in there. So you're going to get a z value of 4, and that's a number between 3.7 and 4.2. Okay? Any questions? All right, maybe we'll do one more quick one, and then I need to talk about extreme value. All right, maybe let's try number 7 over here. So find the local maximums and minimums and saddle points and graph if you can. So, oh boy, oh man. All right, let's do it. So we need to find critical points first, fx. It looks like a product rule. So derivative of the first You know what? I'm going to multiply this out. There'd be 9x squared plus, let's just say 9x squared times e to the y squared minus x squared plus 9y squared e to the y squared minus x squared. So that I'm kind of doing it. Oh, that's not going to help. Crap, sorry. All right, let's do it. Derivative of the first, this would be 9 parentheses. The derivative of the inside is just 2x times the second, e to the y squared minus x squared, plus the first times the derivative of the second. So this is e to the y squared minus x squared times the derivative of the inside, which is going to be 2x negative, the derivative of the power. Now, usually when I ask for derivatives, I don't care to simplify it, but I'm looking forward to, not looking forward to it, but I'm looking forward in that we're going to need to find the second derivative, so it might be nice to simplify this. So I think the way I can simplify this is factor out an e to the y squared minus x squared. That's common to all those terms. And then I have 18x. And then a minus 2 times 9 is 18, x to the third. And then an 18, negative 18 x y squared. And then I have to set this equal to 0. All right, I'm not liking this already. All right, I could factor out an x. That might help a little bit. Let's see. Let's keep working with this. I'm going to eventually set this equal to 0. And so let's factor out an x. And then what I have here left here is 18 minus 18x squared minus 18y squared. Okay, so this might give me some idea that this could possibly be some circular sort of thing. And so either x is equal to 0 or the e to anything is never going to be equal to 0, so I won't even mess with that. And then I have 18 minus 18x squared minus 18y squared is equal to 0. Now, if I bring 18, the x squared and y squared to the other side and divide everything by 18, I'm going to get a unit circle that I'm going to write like this. And then I'll decide later on whether I'm going to want to deal with this symbolically, analytically, or graphically. All right, that was hard. Now let's do the next one. The next one is taking the derivative with respect to y, which is going to give us essentially the same thing. So we have 9 times 2y squared e to the y squared minus x squared. So derivative first times the second plus the first. Times the derivative of the second, e to the y squared minus x squared times negative 2y this time. And doing the same thing we did, I can factor out, Should have factored out an 18 here. Looks like I can factor out an 18y e to the y squared minus x squared. So let's see what happens if I factor out an 18y. Oops, sorry. This should be a y, not a y squared. I'm expecting it to be kind of like a mirror image of the one before that. So 18y e to the xy factored out. That's gone. This negative here will distribute. And then the 18 is gone. The y is gone. So I just have an x squared. And then the same thing over here. Oh, okay. So then that would make this positive and positive, right? Okay, so now, if I'm going to set this equal to 0, I'm going to have y is equal to 0. E to the anything is never going to equal to 0, and I have 1 plus x squared plus y squared equal to 0. Now, if I move things around, I'm going to get x squared plus y squared equals -1. Since the left-hand side is all positive, I'm never going to get this to work. So this has no solutions here. So it looks like I just have this. So my critical points would be combining these two things. I have x is equal to 0, y is equal to 0. So critical points, I have x is equal to 0, y is equal to 0. That's one pair over here if I pair this up. And then if I put y is equal to 0 over here, then I'm going to get x is equal to plus or minus 1. So that's another 2 points. So x is equal to 1, y is equal to 0, and then x is equal to -1, y is equal to 0. So I have 3 critical points that I have to check. And it looks like we're out of time, so maybe I'll let you finish this up. So you need to find the second derivative, and then find that discriminant expression, and then plug these points in. Now, fortunately, these have a lot of zeros in it, so I might make your plugging in a little bit easier, but taking the derivative of these things might be a little bit challenging, so just be careful when you take derivatives of those. Okay? All right. You guys will have a quiz on Thursday. The quiz will be on like tangent plane kind of business. So whenever it is, we talk about that. See you guys.